We are on slide 8, bunnies versus viruses. We are going to look at two different scenarios. Earlier, we encountered a basketball tournament scenario where the number of teams was just decreasing over time, and also trees in the forest that were increasing over time. Both scenarios could be modeled by exponential functions. Today, we are going to watch some more scenarios. I wonder if these are exponential. This video does not have sound, so don't think that you can't hear. Just go along with it. A love story of epic proportions. Oh, of constant proportions. Featuring, two cute little bunnies that are caged up, Buddy and Missy. What do you think is going to happen? Boy meets girl. Uh-oh. Uh-oh. They run away together. So sweet. Love. They're in love. Start a family. Baby bunnies. What'd you say? Koalas? They're feeling bunnies. 1 month later. Oh my. Another month later. Oh no.
That's a constant proportion.
Another month later. Oh. Oh my gosh. Let's keep track. Time and months. Month 0, we have 2 bunnies. Month 1, we have 8 bunnies. How many babies did they have? 6. Okay. All right. Next scenario. What do you think this is about? Oh, a little virus sitting on doorknob. One little COVID sitting on doorknob. What happens when you touch that doorknob?
Virus.
Oh, virus. Another 75. Oh my gosh. So that's how it goes, spreads so fast. Start with 3 little viruses. Oh my gosh. Okay. Do they have the same behavior? So let's answer the question here. How are the scenarios the same? So you can do it on here or the one that I printed out. It's up to you. I'm just going to do it on here. Talk about this out loud. Do the scenarios have the same kind of behavior?
Yes.
Yes? Okay. So do they have the same behavior as the basketball teams and tree population? Which do they have the same behavior of?
The tree.
Tree population, okay. Because why?
Because they both increase.
Because they're increasing, right? Let me make this big. All right, so let's talk about how these two scenarios, the bunnies and viruses, and them compared to each other. So how are the same? How are these two the same? Okay. Both increasing. Over time? Okay. Pull up your mask. Okay, and then how are they different?
One. Aren't together.
Okay. So which one?
The viruses.
Viruses. Increase faster?
Yes.
Okay. All right, so let's look a little bit more in depth on it. We need to find the number of bunnies and viruses for these scenarios if the pattern continues for the time of 3. So time in months is 3, time in days 3. So let's look at this table and let's find out how much it's increasing by each month. So what is the increase here? 6, but what operation? Addition, yeah. Okay, and what about this one? That's 6. So then the next one?
20.
So that'll be 20, okay. And then it's just going up by ones, right? Okay, let's look. So do y'all remember recursive rules? We talked about this. We're going to write it out where we put start and then next. We did this a little bit before Christmas, so it's been a while. You with us? So what did it start with? 2, and then what's the next?
8.
Well, you do now, whatever you have now, plus 6. So whatever you have now, so in month 0 we have 2 now, and then we add 6. Okay, how would we write this as a function rule? A y equals 6x, because this tells us our slope, right? And our b is 2. So 6x plus 2. Cool. So this is our function rule. This is our recursive rule. So let's graph it on here. So x and y, and we're going to write down what x represents. Time in months. And the y-axis represents number of bunnies. Okay, so how should we graph this? What should we put as our x increments? Yeah, so 0, 1, 2, 3. We can go up to 4. And now our y? What do y'all think? 2. 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, I could get 20 in here. Just do that. And so plot it. So 0, 2, 1, 8, 2, 14, 3, 20. Okay, so this is a linear function. Okay, so we can write out here linear function. We have a constant addition of 6. So now we need to find out how many viruses we'd have at 3 days. So let's do the same thing. Let's find out what our pattern is. So what is the pattern for viruses? Times 5 this time. So we need to do 75 times 5. What's 75 times 5?
375.
Y'all agree? Okay. And then the days are increasing by 1. So we need to do the recursive rule. So remember how we did start and then next? We're going to do the same thing. What does it start with?
3
And then what's the next?
times 5.
Yeah, so now times 5. So earlier we said viruses increase faster. And why is that? Because what? Yeah, because it's multiplied by 5. Addition by 6. Multiplied by 5. If you're multiplying something times 5 every single time, that's a lot faster than just adding 6 every time. I always like to think about it as money. If I start out with money and my parents want to times it by 5 every week or every month compared to just adding $6 to my account, whoa, I would want this one so much more, times 5. So let's figure out our function rule. Y equals, well, what are you multiplying 5 times? Remember, we did the rule with our last lesson. So this first one was just 3. But what was the next one? We took what we had and we multiplied times 5, right? 5x. Let's look at the next one. What would the next one be? It's whatever the previous was, 3 times 5. And then what did we do to it to get 75? Times 5 again.
Oh.
Remember this?
Yeah.
Okay. Then what about the next one? It's what we had before.
3 times 5.
Times 5 again.
Would it be 3 times 5 to the x power?
Yes. 3 times 5 to the x power. Because you're multiplying 5 each time. So there was multiplying by 5 before it. And then you have to keep on multiplying times 5 however many times. So this was just 3 by itself. This was 3 times 5. This was 3 times 5 squared. So see the 2 and the 2 here? They correspond because that's our x value. And so the next one is 3 times 5 to the 1, 2, 3. which that is our x value. I need to put a little dot there. There we go. So 3 times 5 to the x power. So what kind of function is this? This one was linear. What kind of function do we have now? Did we talk about it on the last lesson? I don't think we actually named it. It's called exponential function. So it has an exponent for the x value, so it's exponential. Okay, so we've already written the function. So now we're going to graph it. So the x-axis, what does that represent? Yeah, time in days. And what does the y-axis represent?
Oh, number of viruses.
Yeah. So days, we only need to go up to 3. 1, 2, 3. So now is the tricky part because we got to get from 0 to 375 here. So what should we go by? 50? Okay, so that would be, I need 8 of them, right? 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. There we go. All right, so we'll graph it. So 0 is with 3. I'm going to put my numbers here real quick. So 0 is with 3, so it's really, really low. 1 is with 15, still low. 2 is with 75. And 3 is with 375. Is this linear?
No.
No, it goes at a curve. Something like that. All right, so if we look at these, comparing them, it's kind of hard to whenever we are on a different increment here. But this is straight, this is curved. This one is gaining speed really, really fast. It's increasing really, really fast. So linear is a line, exponential is curved. And it just really, really fast zooms up. Okay, we are going to put this in our journal and also take a picture and put it in our digital journal. And then we need to do a problem string. Okay, we are going to do a problem string of multiplying with like bases. So go ahead and title it. We've been talking about exponents. Let's find some more equivalences and simplify some expressions. So just a reminder, a to the b. A is your base, and b is your exponent. So let's do 5 to the third power. My 3 looks bad. So 5 to the 3, what does that mean? How do I find that? Okay. So let's find what that is. How do you work that in your head?
25.
Yeah, 25 times 5, which would be... Okay. About 5 squared times 5. It's the same thing. How do you know it's the same thing? So 25 times 5 again, which is 125. Okay. 5 squared times 5 squared. How do you work that one out in your head?
5 times 5, 25 times 5 times 5.
Mm-hmm. And what is that? Yeah, 625, 625. Okay, are there different ways to write 5 squared times 5 squared? There's some other ways to write that. Yeah. 5 with the exponent of what? 4, yeah. How else could we write it? Mm-hmm. Five squared times 5 squared. Oh, that was the same thing that we had. Yeah. Okay. Okay, let's do 2 to the third power times 3 to the second power. How can we work that one out? Okay. 2 times 2 times 2 times 3 times 3. Okay. And then what do we do? Okay. 8 times 9. 72. Okay, could I say that 2 cubed times 3 squared equals 6 to the 5th?
No.
Why?
It's kind of like this.
Oh, not like bases. Because if I were to do that, that'd be 6 times 6 times 6. Oh, hold on. 1, 2, 3, 4, 5, not 6. So that's 36 times 36 times another 6. Well, we know that's going to be huge, right? We know that's going to be larger than 72. So we know they are not equal. So I'm going to put a line through that equal sign. So I know it's not equal. Okay, let's do 2 squared times 2 cubed. How would we work that out without using our calculator? 2 times 2 times 2 times 2 times 2. Okay. So 2 squared, that equals
4,
4. 2 cubed,
8.
8. How could we simplify this without actually working out? What would that be?
2.
To the exponent of 5. Good. Okay, what about 2 to the a times 2 to the b? Okay, what does that equal?
4 to the AB.
Okay, 4 to the ab. What do y'all think? Huh?
Oh, yeah.
Do y'all agree or disagree?
Isn't it just the same?
What do you mean the same?
Just 2 and 2.
Let's look at this one. This is, let's say that a is 2 and b is 3. What did we do with the base?
We left it.
Okay, so same base. And what did we do with the exponents? Combine them with what operation? Yeah, so add exponents. So we've got to do the same thing here. So do you want to change your answer?
No. Yeah.
So what would the answer be?
2.
2 to the, what's the exponent?
AB.
AB? But isn't it supposed to be addition? What does AB mean? Yeah. Can we just write it as A plus B? Yeah, we can do that. Because what does 2 to the A mean? It means 2 times 2 times 2, da 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 da, 2 times. How many times? However many times that A is, right? So A times. And then the 2 to the B means 2 times itself, B times. So we would have to add how many times there are here to how many times they are here. And that would be what our new exponent is. So this means 2 to the A plus B. So the rule is A to the X times X to the A times X to the B. How would we write that?
Wait, instead of multiplying, once you add it,
Yes. But we're multiplying here, and we're multiplying these, but we're adding our exponents.
oh, okay.
So if I have X to the A times X to the B, what would that be? X to the A plus B. That's right. So here are 2 problems for y'all to do. Yep.
Should I do the next page?
Yeah. Okay, so this is your homework. These 2 simple problems, you're simplifying them.